Hi students, let's see if we can solve one of the critical issues that you have to confront here in the CSD subject. And I see that you are having difficulties in understanding this, the translation from a plan, for example, a plan that you have laid out by means of the plan C2 ideas, a hierarchical schematic. So how to translate this plan into a VHDL file? That's the point. And we will do that using an example, any example from the website, from digsys web. Let's, for example, review or do that exercise using the arithmetic circuit, the 10-bit adder subtractor for integer numbers in complement and choose complement that is available in the digsys pages, right? So the objective of this tutorial is very simple. Let's practice step by step how to translate a schematic that is going to consist of, as you see in the picture, on components, signals, and logic into VHDL. So, and you know that this is the necessary thing that you have to go through to translate from the planning to the development when you are just in the middle of the design flow for projects. So this is the very idea here. You are planning, you have ideas, concepts, and sketches in your mind, and then in the end, after some time, you have a schematic in a sheet of paper, and this schematic is very well annotated. Like the one in the picture, you see, the one here is very well annotated. You have the chip reference, you have every single name of every single pin, you have the signals like this one Q, the other one which is called T. Every single output has a right name. All right. So you've got that thing. So in the end, what you want is to get this schematic translated to a top VHDL file, something that has to have a name immediately as selectable adder subtracted 10-bit VHD. This is the picture. All right, this is the name, selectable adder subtracted 10b and VHD. You know that the full project will consist of many more files because every component has an internal design in one way or another. But if you are talking about the translation of the schematic to a VHDL file, this is what is recording about. We will find something similar to copy and adapt, which may be any other plan C2 circuit in the web, because it's the pattern and the way to go through is the same all the time. So you do that one time and it's forever, for all your life. The next step is to rename and save the file in the right location. And then, take your time. Probably more than half an hour, but in the end you will modify the circuit inherited from the example, and after a final review you will get what you want, which is the selectable adder subtracted 10-bit VHD. That is the perfect equivalent of this top entity that you have in your sheet of paper, right? So let's go and see how to proceed from the very beginning. So the example that we will develop is an arithmetic circuit. So if you have to start, it's going to be something from P3 or P4. But because it's a two complemented circuit to work with integers expressed like that, it has to be in P4. So probably the circuit, that one, the other subtractor 10-bit, and the selectable one has to be something that you find here in P4. Or perhaps, it is something that you can find in the current course, for example, in the specifications of the PLA, probably something that you have to do, like the PLA, this preliminary lab assignment, the 1.2. So this is a kind of a selected device, and so you see you have a lot of projects here to go one after the other. So I guess that the project 4 is about comparators, but the project 6, you see, it's that one that you are interested in. This is the plan that we have in mind, right? So it is here. In case you get lost and you want to find the circuit, is here. This is the, you know, the plan 1.1.2 on arithmetic circuits. And down there, it happens that the project 6 is the one that we have in mind, the selectable other subtracted 12-bit. So you see, you have this idea, first of all, ideas on how to build a circuit, but that's not the object of the project now. We've done that job, and this is the plan that you have in mind, right? This is what has to be converted precisely into a VHDL file, because you will continue the project developing this thing and then testing if it is really a selectable adder and subtractor. So which means that it's going to be able to operate with two types of numbers. This is the n input for selecting radix 2 or integers, and in addition to this, it will be able to have two operations to perform additions or subtractions. So in the end, this is what you invented. So let's go to the translation. All right. So what is the circuit? It is a single component and then some logic and some signal. So what kind of component you've got here? Another 10-bit, right? So probably you will find something similar in P3 when you talk about others. So that's the place you have to go. You can take any one, but that one is going to be right for you. So let's go to P3, right? And get it as it is from any of the tutorials. For example, if this is a 10-bit adder, you better go and fetch in P3 the 8-bit adder, right? It's going to be good for you. So an auth, it's going to be an auth. So you go planning in this P3 and development, and you've got the other 4-bit, which is okay, but let's see if you have the other 8-bit the same. You see, this is the other 8-bit. So this is okay. You can save it as with the right name in the right folder, okay? So let's invent in the right place the file selectable at subtract 10-bit and copy the file in this selectable other subtracted 10-bit, okay? So the other 10-bit have something like save the link as in the CSD before selectable. So now is the time for changing the name. That's it. So now you can go to this folder and work here very well, right? So because you can just edit the file with the Notepad++, and now it's time for starting the edition of this file to be the one that we like. So let's just start with the comment section. An example of a 10-bit adder and subtractor using a hierarchical structure. This VHDL is the translation of this picture that you have seen here. So let me click it that way. Exercise P4, CSD, arithmetic circuits, choose complement. So now it's not going to be another 8-bit, but something like a selectable. Let's first of all organize the entity, because this is easy, you know, it's the entity is the top circuit that you see in the dotted lines. Selectable, other, subtractor, 10-bit. So the entity has to be copied here, the entity name, and entity, and architecture of this entity is like this, but you know, A, B happens to be 9 down to 0, carry in, standard logic input, S, the same, 9 down to 0. Then there is nothing like a carry in here. It is N, perhaps. And then there is an OP. Oh, that's another input, N. Control C, so that's another one. It's going to be OP. And then the R is the result vector. There is nothing like carry out in the picture. You see, what you have to have in one hand is the printing of this picture. So A, B, O, P, and N, the inputs. And then S, R. So you've got here R and S, standard logic output. And perhaps you'd rather copy another one. Z and overflow. Result, sign, overflow, and 0. Alright. So that's the entity, which is nothing but what you see in the dotted line. Ports, input and output ports. There is also the carry out I see here, right? Because, why? Yes, because it is another when operating with radix 2 numbers, so you have to add as well the carry out. That's it. Carry out is another output, Z, overflow, S, the R, A and B, N and OP. So this is the entity. And now the architecture. What happens with the architecture, the hierarchical architecture plan C2? So that has to be modified naturally, because this is the one belonging to a similar circuit. So how many components you are here? Okay, it's going to be another 10-bit, the component that we have to use. So let's declare it. And the declaration of this component is here. AB carry in, and then the S, the carry out. Then there is another one, which is the carry out 9, I guess. So this is the other 10-bit, and the Z the same. So output, that's the component. And then there is not a single, there is not another one. So the component other 1 bit has to be deleted. And then the signals. How many signals you see in this picture? T, Q, C9, C10. So let's name them all. C9, C10, P, or Q, T, L, for instance. That's okay. And if you like, you can annotate them all in a single line, or you can continue with another line, right? There is no vector signals here, I see, but another name, which V, named like this, V, C9, C10, key. Yes, he is a vector, so this is key. Standard logic vector, 10 down to 0, so this is L and B. W is the same, another name for a signal, this time a single wire again. So you will write W. So those are all the signals, wires and cables in the picture. T, Q, C9, C10, L, V, W, and K, right? That's all. The chip 1 is the other 10-bit, and then there is some logic that we will implement in an equation. So now let's begin with the instantiation. The chip 1, it's this chip, other 10-bit. So let's first of all copy the names in the left side. Okay, so carry in, then carry out, then carry out 9, then Z, and S is not here, right? S is not here, so you can delete that, and you can delete the result. S, yes, S is that one, and then there is Z. That's it. So now let's pay attention to the signals where these component pins are connected. For example, the B is connected to the key, and this is 9 down to 0, full cable. So B is connected to key, and because it's complete vector, you can delete it that way. So just the 10 wires, all the cable, right? Now what else? A is A, so you have to do nothing here, but A equal A. Alright, A, 10 wires again, goes to A. Then B goes to key. Okay, and then carry in goes to W. That goes next. Carry in goes to connected to the wire W. And then the carry out goes connected to C10. Right, carry now C9, and then S. Well, here you can subdivide that in 2 sections. Let's make it, for example, like this: 8 down to 0, right? These 9 wires. Let's put that the same. Let's arrange that. That's it. That kind of details are very important to see if everything is alright. So there is no problem in writing tabs. Make room for everything to be clear. So S, 8 down to 0, goes to R. 8 down to 0. Then there is something else. This S9 goes to connected to the signal Q. So this is S. Okay, the W is like this. So now let's delete something else, and let's organize, for example, the K, right? The K wire or cable, 10 times a short. So you may like to do it like this. Let's fix it as a command now. K is going to be what? B short, right? This way. B short. What exactly? W, right? And that I'm not sure about this is because, you know, let's fix that as a comment, and there is another way that is going to work for certain. If you have doubts about this, you see I'm inventing the syntax now, but this is something that is not recommendable. You know, you better do it in some way or another that you know for certain that is going to work. All right, and the way that you know is going to work is wire by wire. So you take that and you do it like this, or like this. You know, key 9, that's the calculable name, is going to be the V9, short W, that's for setting. Then you can do that again, V8, key 8, with short with the same W, and then again, and again and again. So this is the 7, the 6, the 5, and then you can continue. So 4, 4, 3, 3, 2, 2, 1, and 0. All the port B shorted with W to control what to do with the K vector. Something like this, you see? Any single B with a short with the same input W to get the K vector, which at the same time, you know, was connected to the B in the chip 1. Right, so those are the 9 gates. Now that the 11 gates that you see here are already here. You can go counting them all, right? So now let's continue on the other side of the chip. For example, V is nothing but what? A buffer, no, a not N. Something like this. Another one. Then what? Well, carry out, perhaps what was here, no, carry out is V and C10. That's it. Then there is another one. L is what? Carry 9, you know, the overflow signal, carry 9, short, carry 10. That's the L. And then, you know, because the L only exists, this overflow only exists when you are performing integer operations, you know, when 0, this is blocked. So this AND here acts as a blocking device, resetting the output overflow when working with radix 2 numbers. So now it is the next thing, or the previous thing, doesn't matter here the order in which you are writing the gates, doesn't matter because all of them are just a second. Overflow is L and N. And then there is something left here, which is the T. It's a buffer. T is now just a buffer, you know. T is a buffer of Q, so you say so. Buffer. And then there is another buffer, which is R9, the one which was left from the, you see here, you instantiated 8 wires from the result. So now the one which is left, the R9, is nothing but S9. No, not S9, sorry, it's the wire Q. Okay? Q is a signal. Q is something that you have declared here, Q, right? A signal. Standard logic signal, a single wire. So now you are practically finalizing this, and this is the S, right? The sign S is Yet again another AND of what? T and N perhaps another time, because you know it's this idea of blocking the sign as you block the overflow when working with radix 2 numbers. So or disabled when working with radix 2 numbers. So I guess that this is the secret that you are liking to find, you see? That's the perfect translation, you know, of this picture. There is nothing else left. And finally, you review it all a little bit, because you know it is easy to have mistakes here, and then perhaps when you go and continue developing this with an EDA tool, perhaps you have more difficulty than now, or perhaps you will not be able to find all the errors now, but so it's a good time to put everything in place and review, okay? Because it's not difficult to do that. You have 1, 2, 3, 4, 5, 6, 7, 8, and 10, 18 gates. So 1, 2, 3, 4, 5, 6, 7, 16, and 17. And a gate is missing. Which one? R is Q, T is Q, another buffer, overflow. Overflow is L, and this short perhaps L, no, this short is here. Then you have carry out. V is the not carry out. Well, everything looks fine. W is, so 1, 2, 3, 4, 5, 6, 7, 8, and then 18. So V is not N. T is Q. That one is the port. S is T and N. Exactly. And then there is the W, which is that one, OP, overflow, OP, and N. That's right. And then the 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. So that's the second. And then so everything looks fine. Okay, so this is the tutorial. You see, in the end, you can come back to you can continue this design flow, because now you have the file that have been translated from the scheme. So that's the beginning of the development process, from which you will finally develop the RTL circuit. So now it's your turn to organize the development using an EDA tool and watch the RTL schematic to see that it's perfectly well like the one that you have translated, right? So that's all. Thank you.